As usual, I will tell about creation of efficient multi-enzymatic complexes for sugars production from renewable feedstocks. Next. Next. In fact, just a few days ago started the big project led by Corporation of Biotech with the target to create a pilot plant to convert lignocellulosic feedstocks to sugars, and somewhere here. This is a formal target. The informal target is to produce a butanol, and we are busy in this project, in this session. We need to produce the enzymes, and we need to use the enzymes to produce sugars. So our feedstock are very different. I wouldn't tell you what is the big difference among those feedstocks, but the main idea is we need to select the enzymes to convert polysaccharides, which is cellulose mainly, and chemicellulose, like xylene 1N, to C5, C6 sugars. And we need to operate among the enzymes of cellulose complex like N-glucanases, cell biohydrolases, and beta-glucosidases. And plus, we need to operate with isonases, mononases, and accessory enzymes to convert the hemicelluloses. So, ideally, for each kind of feedstock, we need to create the own enzymatic complex. Next. And I would say that the first bottleneck. We need to penetrate a first bottleneck in long growth. So this is a pre-treatment. All of us know that initial raw material are very rigid and not possible to hydrolyze by enzymes, the untreated material. So the corporation next of biotech are dealing with dry milling. This is a lab scale dry mill activator, and a larger scale dry mill activator. And this is very efficient. This is less efficient, so the main problem is how to keep the same efficiency during the scaling up processes. Next. But anyhow, this is initial Aspen chips, and this is a very thin powder after milling, so this powder is activated. It's very easy to check it when you mix those powder with water. Very easy to see the behavior of this powder is not the same as the normal powder. Very easy to see the difference. Next. We compare those dry milling efficiency of dry milling pretreatment with another kind of pretreatments like steam explosion or organozole, or this is high kappa number cellulosic pulp. It's pulp from pulp and paper industry. So the low bars reflect the reaction ability of non-treated material, and the red bars, big bars, reflect the reaction ability after pretreatment. So you see that dry milling gives quite high efficiency. So this is results of sugar yield in the processes of saccharification at particular conditions of those treated and non-treated material. And another bottleneck is the enzymes, because the enzymes cost money, and not possible to produce the enzymes for the price of cost of water. And we operate with two kind of mutants, mutated strains producer of cellulases, penicillium strains and trichodermal strains. In fact, we started to work with these strains many years ago in the past, and we did it together in collaboration with Institute of Biotechnology in Leipzig, with German partners. Now it's closed, but the partnership still exists. So, next slide. And when we compare the saccharification ability or activity of penicillium enzymes, we found that it's a better, higher activity compared to trichodermal enzymes. And I would say that most of companies, most of, let's say, cellulose world people working with trichodermal enzymes, but because of some reasons we started dealing with penicillium enzymes and recognize that saccharification ability is about twice higher than trichodermal enzymes. This is conversion rate of steam exploded Douglas fuel. This is time of the processes of conversion. Next. And we put, let's say, our nose deeply to the problem why penicillium enzymes are more active. We purify all the enzymes from trichoderma, all the enzymes from penicillium, which are secreted out of cells. We found in cell biohydrolase 1 that has quite high specific activity compared with another enzyme. This is glucose yield from bacterial corn hops when we use single individual enzymes for saccharification of the substrate. So in general, the difference, the reasons of high saccharification activity of penicillin enzymatic complex is high specific activity of the penicillinases, diverse and more efficient enzymatic cocktail produced by the fungi, the production of some of beta-glucosidase of cell bodies, and trichoderma is very poor producer of cell bodies, and we recognize less inhibition by lignin and lignin residues of penicillin enzymes, and we see less unproductive absorption of penicillin enzymes and cellulose. And we, sometime in the past, we run a quite efficient mutation program with initial penicillin strain, which we obtained from German partners. So we run several successful steps, and we improved the productivity by 5 times. And we found the strain here, which is derepressed, and we can feed glucose or sugars during fermentation. And at the same time, we got those mutated strain for genetic engineers. It tells that this is a host strain. So we decided to use this very productive penicillin strain, which already produced very efficient cellulose complex. We decided to use it like a host system to try to improve the cellulase or enzyme complex. So we use we have a recipient strain, host strain, and we use at least 2 promoters, CBH1, which is very strong, inducible promoters, and histone promoter, which is weak, more weaker and not inducible, and we express a lot of the enzymes. And this is not a full list. For example, for people, let's say from Manchurians, it will be interesting that we can express pectinases, amylinases, alpha-galactosidases, glucoside. This is enzyme which can be used and used in the food industry quite efficiently. And so it's a few opportunities. We can expect a few results, several results. One result could be when we use very strong promoter, we can obtain probably the producer of one single enzyme, target enzyme, because other enzymes, secret enzymes will be contaminated. Or we also can expect that we can produce the basal cellulase complex, plus some of target enzyme, and by using histone promoter, we expect to have such kind of situation. Next. And just first step of cloning and expression of beta-glucosidases in penicillin kinase and show us that we go to situation number 1, so we get a producer, very strong producer of beta-glucosidase. So this is composition of the enzymes produced by host strain. This is cell biohydrolase 1, 2, N-gluconase, etc. Only 1% of beta-glucosidase, but we got 80% of total secreted pool of the proteins belong to beta-glucosidase. So just only enzyme producer, and this is saccharification results yield of reducing sugar during time when it's saccharification dry milk soft food. And this is how the enzymes from host strain works, and we add the beta-glucosidase produced from those recombinant strain, and we improve about twice the saccharification activity. Then we clone and express a number of the enzymes trying to boost, to improve. They already existed, already produced cellulase and enzymatic complex penicillium, so we clone and express additional cell biohydrolase and N-gluconases from trichoderma to penicillium. We use penicillium kinase and xylanase to clone penicillium tuberculosum. We also express xylanase and malonase from trichoderma and penicillium tuberculosum. Next. And we got, we come to quite quite good improvement of saccharification ability. So this is results of this is a sugar yield during the time of hydrolysis of dry milled hardwood by let's say competitive preparations from novozymes and engineering core, and this is control, and this is a new expressed. This is products produced by new recombinant strains. So we see in any dosage of enzyme or protein, 2 milligram of protein per gram of substrate, 5 and 10 milligram per gram, and we always see that a new recombinant products gave better results than competitive products. So really come boosting effect for existing similar strains. So it's the same for dry milled bagasse. So again, we got better yield, higher yield, and higher initial velocity, higher velocity in processes. Next. And now we come to situation number 2. So we are lucky. So this is a composition of control of host strain, of enzymes produced by host strain, and this is composition of the enzymes produced by recombinant strain. So we are lucky we keep intact the main saccharification enzymes, CBH1, CBH2, but we add some xylanase or endoglucanase 4, which is enhancer, to complex, but we keep intact, almost intact the initial enzymatic complex. Next. And using a histone promoter, we can express at least 3 enzymes to boost. And the next. And even in this case, we got quite more efficient enzymatic complexes, enzymatic recombinant complexes produced by recombinant strains. So this is just final yield of sugars from after saccharification of dry milled hardwood and bagasse. Bagasse is hardwood. So we improve the yield comparatively with the, for example, host strain which is control compared with the commercial enzymes produced by competitors. And in this case, using histone promoter, we came to situation number 3. So we just keep intact again the powerful enzymatic complex of host strain, but we add some, in this case, beta-glucosidase. It was 1%, as you remember. We got to 13% beta-glucosidase, content of beta-glucosidase in the protein pool secreted by recombinant strain. And now we finish the program and we can express 2 or 3 genes together. So it's the same transformation act. We add not one plasmid for transformation with target gene, but 2, 3, and potentially more. And then we need to screen very carefully for transformers, which here 2 or 3 additional activities. So we did that. Yes. And you see this results of screening of transformers. This is saccharification of wood, dry milled bagasse, and this is control. This is a yield of reducing sugars using the control strain, which is host strain. And here is the yield of sugars by the enzymes produced by recombinant strains, and you see that here, this is target recombinant strain. And now we finish this program. We need to make ourselves ready to work with this quite ambitious project to produce sugars and butanol. So we can run several fermentations using the strains. Host strain or recombinant strain, which produce only 1 additional enzyme, so we need to run a number of fermentations. Then we need to mix enzymes and get enzymatic complex, most efficient enzymatic complex to choose route segregation of selected feedstocks. Or next and last, I guess, we can use 1 recombinant strains which carry a number of genes which produce a number of expressed enzymes, so we need to run on 1 fermentation, and we get in this fermentation multi-enzymatic complex adapted for the cellulose feedstock. Okay, thank you very much.